So this is kind of looking at, this is helpful in organic, particularly when we get to Lewis acids, but right here, acid strength and molecular structure, if you have a generic formula, you can look and be like, oh, based on how these two atoms and ions are going to interact with each other, you can kind of make a prediction about whether they're going to be strong, weak, or somewhere kind of in between. So if you have this generic formula, hydrogen with a Y anion, this is not yttrium here, it's just a generic. So we're talking about binary acids, so like HCl. All right? So in order for it to be an acid, this bond must be polarized. So it's got to be a polar bond. What's a polar bond? It's a covalent bond, yes. So electrons are shared, and one of them is stingy. So they're not shared equally. So the H has to be positive, or you can say more positive, in order for it to be actually acidic. So here, even if you just look at, just put some charges on there for charge balance. This is the only one that's going to make an acid. Because the CH bond is basically nonpolar when they share electrons. Now, also when you have a binary acid, so first of all, it's got to be polarized, the H has to be positive. Because if the H comes off and makes H negative ions in solution, is that going to cause acidity? No, we look for H plus, so this makes sense. We need H positive ions in solution. Can we get them? We can look at the molecule structure to see. So is it polarized? And then you can look at the bond strength. Again, most of these you're probably going to have to look up the bond strength, which doesn't particularly help you very much. But if you have a strong, like a stronger bond between these, so if this is a real strong bond, do you think that this hydrogen is going to want to come off? No, it's going to hold on to it. Exactly. So if you have the stronger the bond between these two, the weaker the acid will be. Case in point, HF. So hydrogen and fluorine. Fluorine's going to be negative, H is positive. And fluorine is super electronegative, so it's going to really hold on to this. It's a very strong bond, which is why hydrofluoric acid is not strong, it's weak. Now with our other acids, oxyacids, so here we're talking about carbonic, sulfuric, phosphoric, chloric, nitric. Here you have a hydrogen. If you draw a Lewis structure, here you're going to have a hydrogen that's bonded to an oxygen that's going to be bonded to your generic atom. What matters here is the more electronegative the Y is. So here, when this is more electronegative, that is going to make a stronger acid. Because it makes this bond more polar. This one here. This is the one that needs to break in order to release the proton. So when this is really electronegative, it's going to pull the electrons away from the oxygen, and the oxygen is going to say, wait, I want the electrons, and it's going to pull them away from the hydrogen. Hydrogen comes off more easily. Now, the number of oxygen atoms also counts how many oxygen atoms you have. The more oxygen atoms you have, the stronger the acid. Meaning here, H2SO4, this is sulfuric acid. That is a strong acid. Sulfurous acid with one less oxygen is a weak acid. Questions? All right, those are mostly just conceptual, not really working problems off of them. Now here, I talked about Lewis acids and bases at the beginning of the chapter. The book doesn't talk about them until the very end. Again, if you're going to be taking organic, please keep this handout. You will appreciate it. So according to the Lewis definition, acids are electron pair acceptors. They are electron pair acceptors because when you draw the Lewis structure and you start looking at hybridization and all those things that we did at the end of 170, you will see that it actually has an empty orbital available. So some of those that have incomplete octets, like boron, because boron's happy with 6, well, it has an empty shell. It can take 2 more electrons. Or if it doesn't already have an incomplete octet, it can actually rearrange the electrons within the structure. So again, most of the time you're going to have to be drawing Lewis structures when you do this. We're not going to get into this beyond this little section in this class, but it will be important if you're moving on. So these molecules might be able to rearrange electrons in order to create an empty orbital. Carbon dioxide can do that. And so if they create an empty orbital, that can then accept an electron pair. The base, on the other hand, is your electron pair donor. So when you look at these, you're looking at a Lewis structure and you're looking for lone pairs of electrons. So if there's a lone pair, it can go somewhere. When you start drawing reaction mechanisms, you'll be drawing where the electrons are going. Using this definition and Lewis structures, it significantly expands what we consider acids. The take-home message here, and then I'm going to draw you a couple of mechanisms just so you can at least be introduced to them. You will not be asked to draw mechanisms on the test, but just so you can say you've at least seen one example before. Anytime you have a Lewis acid with a Lewis base, you are going to form a covalent bond. All right. So here, let me draw, I'm just going to do one of these. If you have boron with all its electrons, do you see boron has an incomplete octet? And we said it's stable, it's happy like that. Well, we can take This is not an O, this is just an empty circle. We can take an organic compound, like, this is a ketone. CH2, O, there's your lone pairs. CH2, CH3. I know I didn't draw the structure perfectly, but what ends up happening, and this is what you'll be doing if you've got to go on to organic chemistry, is you figure out where the electrons are going. The only lone pairs here are these. Do we agree? Yes. So these electrons, and you draw your arrow just in the middle, and they're going to go right there. Get used to drawing reaction mechanisms. So then you're going to redraw your molecule with this new bond that you just formed. So CH2, there's your O. Now I connected this using the top pair of electrons, so that's where my, and if you're like, this is absolutely ridiculously crazy, you're right. It is strange. This is, you are not drawing mechanisms on the test. But if you're going into chemical engineering, you need to get used to drawing mechanisms. So I'm going to do one more for you. So here, let's use water. If we use water, what is water here? Is water an acid or a base? Base. It's a base because it has lone pairs to donate. So water is going to be the Lewis base. And let's mix this with carbon dioxide. Does carbon dioxide have any empty orbitals? Yeah. It will. It doesn't right now, but it can rearrange. So here's where drawing mechanisms is important, and you're going to go, this is absolutely crazy. This is what I did for the entire duration of my Organic 2 class, was carbonyl chemistry. So one of these pairs of oxygens is going to attack this double bond here. So it's going to go on carbon. Well, carbon can't have 10 electrons, so it's going to send them up to this oxygen. You're going to go, wait a minute, what in the world? Let's draw what we've done so far. Here we have our oxygen, which is now stuck to our carbon, so it's got its hydrogens on it. This, we made a single bond. There, here's your double bond. O still down there. Whoa, we totally changed this structure, didn't we? All right, you know what? It's still not happy, because if you go and you put in formal charges, you're gonna go, this oxygen is a -1, this carbon is a 0, this oxygen still has a lone pair, is a +1. So we can fix that. So this oxygen is gonna go steal a hydrogen. And the hydrogen says, okay, I'll put my electrons back to oxygen. Again, if this is over your head, that's okay, it's not on the test, but it is important. But that is how you end up with C double bond, nope, that's a single bond. I drew it. Yes.
So are the bonds only going to like change oxygen only?
Yeah, oxygens and hydrogens. So that's how you end up with, there, that's a double bond O. I drew my stuff wrong. But that's how you end up with an acid. C double bond O, single bond OH. That's it.